We all take it for granted that if you drop something, it falls. But what about in a galaxy a billion light years away? Does gravity work the exact same way over there? It sounds like a pretty simple question, right? But it's actually one of the biggest, most profound assumptions in all of science. So let's dive in and investigate.
So that's the big question we're tackling today. Are the foundational laws of physics exactly the same everywhere in space and all throughout time? Is the universe's rulebook, identical from cover to cover? Or could there be some weird footnotes, some exceptions scribbled in the margins of spacetime? We're basically going on a cosmic detective story to figure it out.
All right, first stop, a little history. Because this idea that one set of rules governs everything, well, it's actually a pretty new idea. For most of human history, people thought the cosmos was totally split in two.
And this really shows you what a revolution in thinking this was. For centuries, everyone just went with Aristotle's idea. You had two totally different worlds. There was Earth, the terrestrial realm, where stuff falls down, and then there were the heavens, the celestial realm, where perfect objects just moved in perfect circles forever. But then, bam, Isaac Newton comes along and just shatters that entire concept. He realized the exact same force that pulls an apple to the ground is what's keeping the moon locked in its orbit. All of a sudden, it wasn't two worlds anymore. It was one universe with one rulebook.
And from there, this brilliant idea just kept picking up speed, kind of snowballing. You had Maxwell showing that electricity and magnetism. Yep, just two sides of the same universal coin. Then, of course, Einstein steps in and redefines gravity itself as this property of space-time that works the same way everywhere. The pattern was becoming crystal clear. The universe loves to unify its rules.
Okay, so that's the history. But what's the actual evidence that these laws are the same everywhere? Well, it turns out astronomers have been building a case for centuries, and let me tell you, it is incredibly strong. And one of our absolute best clues comes from ancient starlight. So, when we capture light from a galaxy that's billions of light years away and we spread it out, kind of like a rainbow, we can see these unique barcodes for different elements. We call them spectral fingerprints. And what's amazing is that the fingerprint for, say, hydrogen in that distant galaxy looks identical to the one we see in a lab right here on Earth. That's a huge clue. It tells us the laws of electromagnetism and quantum mechanics, the very rules that create those fingerprints, have been rock solid across billions of years and unimaginable distances. And then there's this. This is literally the universe's baby picture. It's the fossilized light from just 380,000 years after the Big Bang. And the most mind-blowing thing about it, it's almost perfectly smooth. The temperature is basically the exact same everywhere you look across the entire sky. That incredible uniformity is just about the best evidence we have that right from the get-go, the universe was playing by the same set of rules in all directions.
Okay, check this out. Imagine you had a special kind of light bulb, and no matter where you put it in the universe, it always had the exact same brightness, like a perfect 100-watt bulb. Well, you could use how dim it appears to figure out how far away it is, right? That's exactly what certain types of exploding stars, these type 1I supernovae, are for us. They're our cosmic standard candles. They explode with such a consistent, predictable brightness that it strongly suggests the laws of nuclear physics driving those explosions are the same everywhere, whether it's in our cosmic backyard or way, way on the other side of the universe.
Here's another great piece of evidence. Think of it like a recipe. Scientists have this recipe for the early universe based on the laws of physics as we know them. And this recipe predicts the exact amounts of light elements, like hydrogen and helium, that should have been cooked up in the first few minutes after the Big Bang. And guess what? When we go and look at the oldest stars and galaxies, the amounts we observe match the recipe perfectly. The only way the recipe works is if the laws of physics were the same back then.
So when you add it all up, the ancient starlight, the universe's baby picture, those cosmic light bulbs, the recipe for the elements, the evidence looks absolutely conclusive. The case for universal laws seems totally airtight.
So, case closed, right? We're done here?
Well, not quite. Because in science, it's often the things that don't quite fit that lead to the biggest breakthroughs.
So, let's talk about those. Despite all that overwhelming evidence, there are some really nagging puzzles out there. Some subtle cracks in our otherwise perfect cosmic picture. And, well, here's the elephant in the room. This chart says it all, really. Everything we understand, everything we can see and test, all the stars, galaxies, planets, you and me, all of that normal matter only makes up about 5% of the universe. Just 5%.
The other 95% is this mysterious stuff we call dark matter and dark energy. And here's the kicker. We can't explain them with our current rulebook. At all. So that forces a huge question. Are we just missing a giant chapter of the physics textbook, or are the laws we think we know not the whole story?
And it's not just the dark stuff. There are other little tensions, these annoying discrepancies. For example, when we measure how fast the universe is expanding right now, we get one number. But when we use our model of the early universe to predict what that number should be, we get a slightly different one. We call it the Hubble tension, and it's a big deal. Then there's the lithium problem. Our Big Bang recipe predicts a little more of a certain kind of lithium than we actually see in the oldest stars. These are all loose threads that scientists can't stop pulling at.
So you see, this isn't just some abstract academic debate. The answer to this question strikes at the very heart of how we do science. And that's why we're building some absolutely incredible new tools to finally get to the bottom of it. And this really gets to why this is so important. The assumption that physical laws are the same everywhere. That's a foundational pillar of science itself. I mean, think about it. Without that assumption, the whole field of cosmology just collapses. We couldn't trust anything we learn from the light of a distant star because who's to say it's playing by the same rules? The entire scientific enterprise basically rests on this one simple, powerful idea. But we're not just hoping for the best. We're actively pushing the boundaries to find answers. We've got next-gen powerhouses like the James Webb Space Telescope peering deeper into cosmic history than ever before. We're using gravitational waves to test gravity in the most extreme environments in the universe, like around black holes. And we have these massive new surveys that are mapping out billions of galaxies just to look for any tiny inconsistency. We are, right now, stress testing this fundamental assumption like never before.
Which brings us right back to our central mystery. Is our cosmic rulebook pretty much finished, totally consistent from one end of the universe to the other? Or are all these strange puzzles, dark matter, dark energy, those cosmic tensions, are they all just breadcrumbs, hinting that we're just starting to read the fine print of a much deeper, much stranger set of rules? We don't know the answer yet, but the search is definitely on.